Tools of Technology, Overview, Unit 10, Energy Converters.
In the 1970s, when the oil supply from the Middle East was shut off, North America suddenly realized the value of energy and how, in many cases, it's wasted. Since then, the search has been on for new and alternative sources of energy. But the biggest source of energy in this part of the world is not the energy found, it's the energy saved. Saving energy simply means using it as efficiently as possible. There's no shortage of energy in the world. We are completely surrounded by moving air, moving water, energy in the ground. But usually these energy resources are in the wrong form to be useful. For example, thermal energy is fine if you want to melt steel. But if you want to turn a wheel, you need mechanical energy. So energy converters, like engines, are devices that take energy in one form and convert it into another. One kind of energy is put into the converter, another kind of energy comes out, with some energy lost in the process. Here's an example. Lane Garrett takes the free energy of the sun and uses a series of energy converters to clean his swimming pool.
Okay, this is our swimming pool, which works very well except when the wind blows and we get a lot of leaves and debris in the pool. The system that is used to keep the pool clean, little plastic whips that move the debris down toward the drain where it can be sucked up for the filter. The photovoltaic energy that you saw earlier coming in from the modules comes through a cable into a junction box. From the junction box, the DC energy goes directly into a direct current motor. This DC motor, as you can see, runs very efficiently. I can keep my hand on it and it's just warm to the touch. This motor actually has an 88% conversion efficiency of the electrical energy into mechanical shaft speed. Over here, we have a pulley that goes into a direct drive pump. The pulley ratio actually runs the pump at its most efficient speed. And as the amount of sunlight varies, the speed of the motor and hence the speed of the pump will also vary. Brighter sunlight, we run faster and we can pump more water. This gives higher water pressure, makes the whips in the pool go a little bit faster for more efficient cleaning. It also develops the pressure that can go through a large, high flow rate sand filter. And this filters out the dust and small dirt from the pool. Now, as you can see, as the sun is coming up and getting brighter, the motor is running faster and we're pumping more water. To give you an example, this pump will put out 60 gallons a minute under full sun as we have it now. It's really important to keep this pool clean for the various family members because we really enjoy it and we like to have a nice, clean, healthy pool. The family thoroughly enjoys this pool. Go on, go ahead.
Energy conversion is not a new idea. In fact, just about every device you've seen so far in this entire video series has been an energy converter of some kind. Energy converters appear in mechanical, fluid, electrical, and thermal systems. To divide them, we will class them according to the type of energy on the input side. So, for example, a mechanical energy converter, like a piston pump, takes mechanical energy and converts it into fluid energy. A fluid energy converter, like a windmill, converts the fluid energy of the wind into mechanical, then electrical energy. An electric heater is an electrical converter because it converts electrical energy into thermal energy. And a thermal converter, like an internal combustion engine, converts thermal energy of burning fuel into the mechanical energy of spinning wheels. Of course, there are many combinations, but in each case, the energy in is different from the energy out. The important lesson for a technician is high efficiency, making sure that when a device converts energy, it does so with minimum loss. Listen again to Jerry Allen, whom you met in our unit on energy, and see how he identified the inefficiencies of his coal-fired generating station, which converts thermal energy into electricity.
One interesting point to remember about a coal-fired generating station such as this is that we don't really create any energy at all. We really take one form of energy, potential chemical energy in the form of coal, and convert that to a more useful form, electrical energy, that's more helpful to the consumer at home. The process occurs in several different stages. First, in the boiler, the coal is burned, releasing heat energy. So we have a conversion from potential chemical energy to heat energy. That heat energy is transferred to water, which converts it to steam, and the steam in turn passes through the blades of a turbine, which converts that heat energy into mechanical energy or rotational kinetic energy. That mechanical energy is converted to electrical energy by means of a generator, which is coupled directly to the turbine. Once we have electrical energy, we distribute it around the countryside. It's available to the consumer to use in whatever form he decides is most suitable. This chunk of coal has a heating value of about 8,000 British thermal units per pound. Of that energy, only about 35% of it is actually available as electric energy when the process is completed. The reason for that is that there are several losses that occur in the conversion process. First of all, in the combustion of the coal, approximately 15% of the energy is lost due to inefficiencies in the boiler, primarily due to hot air and hot gases leaving the furnace out the stacks. There are other losses associated with heat radiation losses from the boiler, as well as auxiliary power consumption in the boiler and the steam plant. The biggest loss by far is the energy that's wasted when the steam must be converted back into water. It's an unfortunate necessity of a thermal cycle that we have to condense the steam, but that condensation process and the related loss of energy actually accounts for more energy loss than we send out on our power lines.
Improving the efficiency of energy conversions, that is, comparing the energy out to the energy in, will be the greatest energy source for the future. For example, the steam engine began the Industrial Revolution. But it's a very inefficient energy converter. Most of the energy from the coal goes up the smokestack. One of the reasons steam locomotives have become obsolete is because the diesel and electric trains are much more efficient to operate. Mother Nature has provided us with abundant energy, but only in a limited number of forms. The number of ways we can convert that energy into more useful forms depends entirely on human ingenuity.